Welcome back everyone to another video in our FE Civil preparation course. In this video, we will learn more about bending stress. Bending stress is our first type of indirect stresses. When a member is under the effect of a bending moment, this causes compression at one side of the cross-section of the beam and tension on the other side of the cross-section. Here we can see a beam under a positive bending moment, trying to get the beam to concave downward. In this case, you can see that the upper side of the beam is trying to get shorter, while the lower side of the beam is trying to get stretched. That's why bending moment will create a compression stress in the upper side of the beam and tensile normal stress in the lower side of the beam. Normal stress distribution at any section is not uniform through the cross-section. Normal stress due to bending moment equals 0 at the centroid, and it increases till it reaches the outer fibers of the beam. The value of the normal stress is calculated by the formula of sigma equals to m multiplied by y over I, where y is the distance between the beam centroid and the point in the beam cross-section where you want to calculate the normal stress, while I is the section moment of inertia. Maximum stresses will be located at the outer surface of the beam as earlier mentioned, hence we can replace y with c, where c is the distance between the centroid and the beam edge. And as I and C are both constant values for any beam section, so if we consider S to be I over C, then stress will equal to M over S. Now let's have an example of this.
So let's check this example. We have this beam here, simply supported with length of 10 meter, and we have uniform distributed load of 75 Newton per meter. We have the dimension of the section, L1 of 6 cm and L2 of 10 cm, as we can see here, and we want to calculate the maximum compressive stress in the beam. First step is to calculate the moment, which equals WL square over 8, which equals 937.5 Newton meter. So now we have the value of the moment, and we know that the stress equals my over I. This is our section. This is 6 cm, and this is 10 cm. And we want to calculate first y and I. Y is the distance between the centroid to the fiber that has the maximum compression, which is the top, based on this moment, which it will be the top fiber. So this is the location of the centroid, because this is rectangle, so it is exactly in the middle, and this distance is 5 cm. Now we want to calculate the value of I. We know that I for a rectangle equals BH cube over 12. Of course, you don't have to memorize these equations. It will all be included in your reference handbook, but it will be useful if you familiarize yourself with it. So we will just substitute now. We have 60 multiplied by 10 power 3 over 12 will equal to 5 multiplied by 10 power 6 millimeter power 4. We transfer the centimeter to millimeter. So now we have the y 5 centimeter, which is 50 millimeter, like we earlier calculated. This means that sigma equals to m, which is 937.5 Newton meter, multiplied by 1000, because we want instead of this meter to be millimeter, multiplied by 50, which is y in millimeter, over I, which is 5 multiplied by 10 power 6. Solving this equation, it will result on stress equaling 9.375 Newton per millimeter square, which is megapascal. So this is it for our video today. Thank you.